So I'm great, just Alex walked in. So the first thing I'll say is that this is work that 3 people have worked on. So Owen, who also just made it, wait, Owen, and then Alex, who just walked in at the back. And what I'm essentially going to talk to you about is the system we use to schedule the conference. So the reason that this session is now and is here, and why you are here, is what I'm about to explain. So I'm a mathematician at Cardiff University. I'm also on the PyCon UK committee, which is my main contribution has been this. I'm one of the organizers of PyDiff, and I'm a core developer of a game theoretic library called Axelrod. This kind of idea of using programming, using mathematics to schedule the conference kind of goes back to a talk that David McIver gave. I don't know if you can see this at the back. So David is the person who gave the keynote on Friday morning, was it? The one with the trees. He's the person who one of the people who writes Hypothesis. And last year he gave a talk about using a particular mathematical tool to schedule things. And probably about a year ago now, maybe a bit less than that, Owen said, "Hey, let's actually do that. Let's actually do that for PyCon." And so this is one of the neat things about this talk is that I'm giving the talk for a project that Owen wrote the first lines of code on, and a little bit later on, Owen's giving a talk where I wrote the first lines of code on. Again, can you guys see that at the back? Does that come up okay at the back? So this is called a linear program. We want to maximize something that has to be a linear, a fine collection of variables, so a linear combination. So for example, if that was x squared, we couldn't use this here. Subject to a bunch of these constraints, so whatever these are, and these can be used to say what type of diet we want to use. So we want to have a particular diet where we get a certain amount of calories, subject to a certain amount of protein, subject to a certain amount of fats, etc., etc. So that's often used as an example in these things. I'll come back to this part of the problem, but I'm going to concentrate on this part. This is essentially the important part of the problem. This is somewhat straightforward once we've got that. So these constraints, what they do is they cut our space of all our dimensions in half. And the way to think about that is if we just look at 2x plus y less than or equal to 4, the other half of that is 2x plus y is greater than 4. And so another way of things that we call these inequalities is half spaces. And so here are the half spaces that I just had in the previous slide, and I've got these arrows to say we've got a line 4 minus 2x, and the particular direction of our inequality says that we want to be on this side of that line. And now what you can see is that these lines cross at particular points, and these points are called vertices. And the actual thing we care about is not the half spaces, is not the lines along which the half spaces intersect, but the actual polygon underneath. This is a polygon. You might be familiar with 2-dimensional polygons, so triangles and things like that, 3-dimensional polygons. But fundamentally, these things can go to much, much higher dimensions, and that's where they are called polytopes. So as long as we've got a finite number of these half spaces, what we're left with is a polytope. And this is the important part, because the actual maximization that happens, and I'll come back to that a little bit later, the actual maximization that happens, you can prove mathematically that that will be at one of these points. It won't be anywhere else, it won't be in the middle, it won't be on the side, it won't be on one of these lines, it'll be at one of these points. And so there's lots of clever algorithms that essentially walk around these polytopes finding the best one. And when I say best, I mean provably there is nothing better. So not really, really good within a certain amount of percentage, or however much percentage, but actually the very, very best. And as of version 0.19, SciPy just released 1.0 the other day, that's cause for celebration. But as of version 0.19, SciPy's got really nice tools for exploring polytopes. So these half spaces, they're actually just the same numbers I had on my inequalities. You can put them in, and as long as you give a feasible point, in essence telling it where it is in the half space, you can create an intersection of half spaces with SciPy, and you can get the coordinates of those red points, of those vertices. So theoretically, you could then evaluate your objective function at all of these points, okay? Which is very much a perfectly good solution approach for the problem of the size I'm considering, but often you have problems with 50 dimensions, so 50 variables, pardon me, which then can imply a huge number of vertices. So actually looking at the polytope itself, which is what we're doing here with SciPy and getting the vertices out, is not a good idea. And this is where the schedule comes in. Obviously, our variables are a bit more complex, but this is a schedule. So we have, for example, 6 rows and 8 columns. Remember those 2 dimensions, because we'll need to keep them in mind. And we have 2 constraints, so that the sum of over the columns, so if I go from here to here and I sum all the numbers, has to be exactly 1. And that's essentially saying that if I have a bunch of events that we need to schedule, so talks, for example, and a bunch of slots in which we can put them, I need, for every event, I need 1 slot that comes up. So, for example, here, the first event goes in the first slot, okay? And then finally, the other constraint is that the sum over the rows, so going down here, so just looking at a particular slot, must be at most 1. So this is saying, for example, I've got an event in this particular slot, so I cannot have another event. But also, we can have a couple of slots that are simply not used, okay? So this is the kind of idea of how it relates to the original problem, which is 2 variables I put up. We can write the same thing down in terms of a schedule. So we're saying, like, we got a lot more variables, right? 8 times 6 of them, and these are our half spaces, okay? That cut up our space into half and give us this polytope underneath. And this leads to a library called Conference Scheduler, and this is the library that Owen wrote the first line's code on, and Alex, Owen, and myself have worked on since. And so it's a pip installable library. It's pretty well documented with a full tutorial as well as much more detailed mathematical background than I'm going over now. And it can be used to schedule actually anything. We had a very brief discussion at some point in the madness of preparing PyCon of perhaps even changing the name from Conference Scheduler to Scheduler, because if you can schedule a conference, you can schedule something else. And the fundamental building blocks of the Conference Scheduler are these 2 classes, slots and events. And once you define your slots and you define your events, within that you define various constraints, and I'll give some examples of that. You can then use it to obtain a schedule. There are more constraints to scheduling a conference than simply all talks must be scheduled and all slots cannot hold more than 1 event. So I can't be speaking here while someone else is speaking on the other side of the room. There are what I like to think of as constraints related to the laws of physics. And this is the idea that perhaps I cannot be here on a Thursday. I couldn't, for example. I was teaching on a Thursday, so I couldn't be here on a Thursday. So to handle this in the most generic way, and this was a big point that we made about Conference Scheduler from the start, is to make a very generic tool that didn't necessarily just work to schedule PyCon, but work to schedule anything. We can create a matrix of constraints on the slots, and this is simply filled with zeros and ones. So for the particular events, so for example, maybe Vince's event, my event, my talk, I cannot be scheduled in these 2 slots. And again, 6 by 8 there. And then that can just be represented using this half space, using this linear inequality, which is if that's 0, then this cannot be 1. But if that's 1, it can be 0 or 1. So then there's other constraints that I think are based on physics, ethics, and life. So this is, for example, the fact that you can't clone me. Students are probably glad of that. If I'm giving a talk now, but I'm also giving another talk, those two talks cannot happen at the same time. And so here, note that this matrix of constraints is a 6 by 6 matrix. So this is just availability between events. All right. So for example, the first event cannot take place at the same time as the second event. And obviously, likewise. That could be because they're by the same person, or for any other reason. But essentially, we have constraints on events and constraints on slots. And then once we do that, we can write down that notion, that real-world constraint, using this linear inequality, this half space. And so this is kind of the pretty much everything about the mathematics that we're dealing with, is that we create anything you might want to happen in a schedule, and we can boil it down to a simple expression like this. And importantly, that's all linear. So there's no squared terms, no log terms, no max terms, nothing like that. And so this is what it looks like in practice. So you go through and you create your slots. So for example, we have a big room. When does it start? What's the duration? Particular session and the capacity. And then we also go through and create events. And we have events that are unavailable at certain slots, but also some events that might be unavailable during other events. So once those events are created, we can do that. And then to come back to this problem, we now have to deal with this, right? Because we can just find a feasible schedule, which is when can a conference work, or we can find a good one. Now, that in essence is two different problems. But as I mentioned before, once we have the actual polytope, finding the best one mathematically is relatively straightforward. So one particular constraint we've got in the conference scheduler, and the way the library is built, in fact, is that you can add multiple different, I said constraint, multiple different objective functions. The one we have is to try and get the overflow in a given room as low as possible. And so the idea being that if we know all our slots and we have the excess capacity, everyone was sent an email asking them to vote on talks, and so we gathered that data. What I could try and do is push this line down. Okay? So in other words, trying to minimize the maximal overflow. But there's a slight problem with that, in that the maximal of a set, that's not a nice linear relationship. And so there's this neat little trick that often is used in linear programming, where you actually minimize a constraint that you create. So this is an artificial constraint that you're trying to minimize, and that is the result of pushing everything down. So we did all this and wrote very well, a very nice library. It's well tested, it's well documented, and then we basically like, okay, I think that was maybe in around April we got to that or something like that, and then we basically like, all right, now we wait to get the calls for papers in and to schedule it. And then EuroPython happened, and then we found out that there was a talk called Scheduling Using Linear Programming EuroPython with Alex Hendorf. Is Alex here? Thought he might make it. Okay. And they use conference schedulers. So like, oh, brilliant! Someone's used the library, and that's great. But the talk goes, you can do this, you can do this. Some guys in Cardiff built the library. We tried to use it, it didn't work. So Owen and I were like, oh, we need to get in touch. We got in touch. They sent us some data. We took a look. And the thing with linear programming is that whilst mathematically it's easy to solve a problem, some problems, once they're very, very constrained, to actually get the optimal solution can take a lot of computer time. That's probably the main difference between a computer scientist and a mathematician, is that mathematicians care about the theory and perhaps not necessarily as much about the practicalities. And so after that, I was like, okay, that's fine. We don't necessarily need to find the optimal solution. we need to find a really, really good one, okay? And so there's a whole branch of mathematics around that, and they use what are called heuristic methods, which are essentially approximate methods that will find a really good solution in a finite amount of time. And there's two of these that I'm going to talk about today and that we ended up implementing in the library. Again, kind of going back to, we found out from EuroPython that something wasn't working, so we thought maybe the size of the problem has happened. So we wrote these heuristics ready to use them. I just really love my dog and wanted a picture of my dog in the slides, but that's me wrestling with my dog. But the main thing, this is a hill, and the first such heuristic algorithm that I'm going to talk about is what's called a hill walking algorithm. And the idea of a hill walking algorithm is that we could be, this is a beautiful hill called Pen y Fan. It's the highest point in Wales. If you've got time to go visit it, I really recommend the walk. If we're here and we want to go down, and we can't see too far ahead, but we know we want to go down. Well, let me say, if we're here and we want to go down, we'd go this way, okay? We'd go down here, and then at this point we'd be like, well, I'm as down as I'm going to go, right? Because I don't want to go up. So I've gone down, this is me at the bottom of the hill. So I'd be here at the bottom of the hill. But of course, well not of course, for those of you who know, if you actually walk down here and then have a rather steep descent, you'd get to the bottom of the hill. And that's the essence of a hill walking algorithm, a hill climbing algorithm. It just finds, at some point, it goes down and it's like, yep, I'm done. I can't go down anymore, all right? And so we have a hill climbing algorithm in the conference scheduler, and what it does is it just tries to reduce the cost function of a particular type. But the problem is we want to find a way of how it would know to go back up before it went down. All right? And this leads to the other point in the... I don't have a photo of me doing metallurgy, and Geraint and I spent, well, and Nicoletta spent a long time trying to figure out what the best emoji for metallurgy was. So, please correct me, my understanding of metallurgy is that you heat something up really, really hot. For example, a bit of metal that you want to turn into a sword. And at the start, it's really, really, really hot. And so when you're smacking it with your hammer, you're not doing so very precisely, right? But you're allowing it to change shape a lot. So as it's very, very hot, it changes shape quite a lot. And then over time, as it cools down, the hitting that you're doing with your hammer becomes more and more precise. In other words, at the start, you kind of let this collection of metal walk around the space that it can take a lot, and then over time it gets a lot smaller. And so that leads to an algorithm called simulated annealing. And this is its implementation, but the idea is that we take a given solution, we make a random change to it, and if it's better, we accept it. If it's worse, we accept it with a small probability, okay? But that probability goes down over time. So in other words, going back to my hill, I might go, if I go left, that's me going up. But if it's at the start of my trip, I'm more likely to go, okay, I'll go up. But over time, if I need to go up, I'll go like, well, you know what, I've been walking for 2 days, I only want to go down now, right? And so that probability goes down. And that's what simulated annealing is. And this is how it's implemented. There's various things going on here. But right here, you see is where, if the delta, so whether or not it's better, is negative, or our temperature is still positive, so the metal is still hot, and a particular random sample has, then okay, sure, go here. But what the important part is, over time, this temperature is cooling down. So there's various ways this cool down can happen, and this is just an exponential cool down that's going down slowly. How we actually do this in practice, we have another library that we've built up called the Conference Scheduler CLI, so the command line tool, that essentially brings everything together and uses the engine underneath. And so we have Iron Cage. Iron Cage is the system you guys have all been speaking to, where you've been putting in your tickets information, things like that, and your talk proposals. From there, we can get the proposals locally. We then have things like, I can't do Thursday afternoon because I'm teaching, and we keep that all in a YAML file. And then what this tool really does, it takes all that and builds those slots and those events for us. It actually does a bit more than that. once it has a schedule, it actually generates the markdown files needed for the website. One of the other things that we did when we implemented Conference Scheduler is that we made use of Pulp, which is the linear programming library in Python, one of the linear programming libraries in Python, to define all our linear constraints and things like that. But we wrote it in such a way that as well as those objects, you can just pass it NumPy arrays. So in fact, and that's why the heuristics work, in fact, you could also use the tool simply to validate a schedule. And I'd suggest that's probably its most valuable tool. That as you're moving around your schedule, instead of going like, does that still work? Have we scheduled someone in 2 places at once? You know, as we forgot to delete a cell or something like that? Well, you can use the tool to use that. In practice, what we did, we used this, we got a schedule, we used the validation, and then at some point we did need to just make sure we were moving fast. And so then we did just flip over to a manual approach. That's all I've got to say. The docs are there, and in fact, everything is under the PyCon UK organization repo, and so you can see that as well as various other tools.
We have some time for questions, so yeah, please.
A lot of times with linear programming, especially scheduling solutions, you get a solution, and it might not be exactly what you want. Is there a possibility that you can get multiple solutions, or you can change the solution and see what? Basically, can you get lots of local optimums?
Yeah. So, just to repeat the question, you know, can you get lots of local optimals, and what do you do when that happens? Is that right? So, you can get lots of local optimal. Because everything is linear, those local optimal will also be optimal in terms of and that's the big point about the linearity. So there's those bumps that the heuristics I mentioned go around. But in a way, we took that into account because you could do 2 things using the library once you've got something you didn't like. You could just say that's not possible. So you could run it again. You could say, you know what, we put Vince on Saturday at 10. Sure, that's theoretically possible, but that's not great. Vince unavailable Saturday at 10, run it again. You could do that. Or you could simply move Vince and swap Vince with Nicoletta or something, and then just use the tool to validate the schedule to see if it was indeed exact.
I was just wondering if there was anything that made any collection of constraints that made something totally unschedulable.
Yes. Yeah, a few times, but that's actually was really nice.
For this conference.
Yeah, there were a few things like that, and that was actually really nice with the tool because someone came in and said, we want something to happen. We ran the tool, we convinced ourselves there wasn't a bug with the tool, and then we were able to say, no, that's not possible, and then we had a little think about it, and we were like, oh yeah, because you want 10 things to happen and there's only room for 9 of them. So, and again, that was quite nice having the tool to be able to just quickly go, that's not possible, we have to change something.
There was some other question?
So you mentioned that it's not, the optimal will be on one of the vertices. Could you give us a highlight of why that is?
So once we have this, right, think of, in this particular example, that objective function as a line that I'm putting on top of this picture, okay? So I'm putting a line on top of this picture, and moving in one direction or another moves that line, right? So if I move this way, the line goes this way. If I move that way, the line goes that way. Does that make sense? And every time I make one of those moves, my objective function is either going up or down. So getting to my optimal solution will correspond to moving this line, yeah? So once you're okay with that getting the objective function corresponds to moving this line, at any point, once I'm there, not quite on a vertex, I'll be able to get it a little bit better by going up to the vertex. But once I get to a vertex, I can't go any further because then I'm outside of the space.
The last question?
That's really good, actually.
Yeah.
I really enjoyed that.
You said there was a problem that you had to stop and think about, and it turned out there were 9 slots for 10 things. So, is there a reason why the program couldn't tell you that, and why you had to figure it out?
The program we could probably put in another layer of checks, but fundamentally what the program does is it passes it off to a solver of the linear program, in which case it would say, this can't happen. But what we do have is a really nice level of logging that comes up and says, we have so many events, so many things. So as soon as it said, there is no solution, we looked at the log and went, oh yeah, you want 10 of those, but there's only 9 of them. So, yeah.
Okay, so we don't have time for any more questions, so let's thank